In this video, we are going to talk about the integral operator as well as line integrals. This is our overview slide, which we will spend about 5 minutes going over before we go over each topic in more detail and with more examples. We will start by talking about integral notation. So we're used to integral notation look like the integral of f of x with respect to x, but to make the integral more of an operation that you perform on a function, we're going to move the integral and the dx together, and then the function we're operating on to the right. The next topic we will talk about are line integrals, which is an example of an integral operator. And so here is what it looks like. This is our operator, and we can use this to act on different types of functions. In particular, the example we will look at are operating on fields, vector fields, using the dot product. And the typical example from physics is the work that a force F performs as it moves along a path C. So here we have the work is equal to this line integral operator dotted with our vector field F. We'll give more details about how this works, including steps for doing the line integral of vector fields when we dot using the dot product. And this is something that should be familiar to you from vector calculus, but we will do a quick review. I have the steps outlined here for line integrals of vector fields using this dot product. First, we parameterize our path. And again, our path, we think of this parameterizing variable t as something like time. So over time, we're moving along the path. Then we calculate c prime of t, which is like calculating velocity. Then we compose our vector field f with c. So the reason why we do this is f is defined, everywhere on the space, but we're not really concerned about the vector field anywhere but as how it pertains to c. So we do this f composed of c, and then we plug into our formula so that our line integral operator dotted with f gives us this formula here, integral from a to b, and the a to b are our limits on t, and then f composed of c dotted with c prime of t dt. We have this example here of calculating work done by following a straight line path given by this force over here, and we will work that out completely in this video. Because parameterization of our path is such an integral step, no pun intended, actually maybe intended, of our process, I do have some parameterization of common curves. That is a line, a circle, a curve given to us by this function y equals f of x, and I also have a bonus one, the helix. So these are the formulas, but we will discuss each of these formulas. Your textbook also mentions this operator here, the line integral operator, not just on how it acts on a force using the dot product, but it has a couple of other definitions. They are mentioned in your textbook, but not really covered, and so we will not be covering them either. We are now ready to proceed with our first topic, integral operation notation. Integral operations are commonly not written in operator form. The common form we have is the integral of f over x is written like this, the integral of f of x dx, and this is considered not to be an operator form because the integral and the operand f of x, so we're integrating f of x, but you can see the integral sign in the dx, it's mixed in with the f of x. In other words, the f of x just kind of inserted itself. So we can, however, put this in operator form by reorganizing the factors. So this integral of f of x dx is equivalent to the integral dx of f of x. In this case now, we consider our integral dx our operator that operates on a function x. So the integral operator is moved to the right, passing through all factors. I don't know why your book keeps saying terms. I think they're factors of the integrand that do not depend on the integration variable. So here, for example, if we have the integral with respect to x of x squared times x plus y squared, here since our integrating term is dx, we can move the y outside of the integral because it doesn't depend on x, assuming y is not a function of x. We can move it out, so we have y squared, our integral with respect to x of x squared x plus y. Our next topic is line integral. The process of taking an integral along a path is called line integration, and our most common or a common example is work that a force performs as it moves along a path C. We notate this work that a force F performs along C in this way. Work is equal to the line integral over C dr dot F. So here we have the integral operator that we had discussed earlier. So now integration is an operation that is performed on this field here, F, on our force F. Then we also have, just looking at this dr vector, if you think about our curve C, this is the path we're following. The r vector is the point we are on that curve C. So maybe at time over here, whatever time this is, we're at this point, and that's represented by this vector r. And our dr then is the vector tangent to r. So r is the displacement vector, dr is our tangent vector. If C is closed on itself, for example, if we're integrating over a circle or any closed curve, right? So we're integrating over a closed curve, then we write the operator with a circle on the integral sign. And looking at this with index notation, so we have W is equal to the integral over our path C dr dot F. So the first thing you want to note is F is a vector field and it has an x, y, and z component. That force, has a component of force in the x, y, and z direction. Also, r is our position vector. It has an x, y, and z component as well. So when we have our dr, we have our dx1, our first coordinate, dx2, our second coordinate, often called y, and dx3, our third coordinate, which is often called z. So the derivative of the first component, second, and third component here, and we dot that with F1, F2, and F3, and the dot product produces a scalar. But also here, we can use our index notation, so over C, dxi, fi. So far, everything we've said is true about the general line integral operator. And now we're going to look at how that operator can act on a vector field using the dot product. Now the steps for line integrals. If you want to find a line integral of a vector field F, so a scalar field, F here is a vector field, you input an xyz coordinate and you get a vector, an xyz coordinate out of it. If it were a scalar field, the line integral would be a little bit different. But here we're discussing vector fields. So the first step is to parameterize your path, C of t. We'll talk about this step a little more in a minute. Then we calculate C prime of t. So remember, if we think of our path as a collection of position vectors, then our C prime of t is sort of like our velocity. Well, it is our velocity. And then we calculate f of C prime. In other words, f is a vector field, and it's defined over the whole space. It's not just defined on the curve, but over an entire space. But because f is moving along this curve, we're only concerned with f as it pertains to the curve. So we compose f with our curve. And then finally, we plug in all these components into our formula. So the integral of C dr dot df is going to be the integral from a to b. A to b are our limits for our parameterization here. Our f composed of c dotted with C prime. I have some of these notes, including the steps for line integrals for vector fields up here so that we can work this example. Calculate the work done by following a straight line path from the Cartesian point 1, 1 to 3, 3 if the force is given by x minus y in the x direction and x plus y in the y direction. Our first step is to parameterize our path, C of t, and I often parameterize my path with the variable t. Sometimes I use theta, we'll come to that in a minute, but I parameterize with the t because I think of my path as something that happens over time, like I'm following this path over time. So L of t tells me where I am on the line at time t. So presumably at t equals 0, I'm at my starting point 1, 1, And as time progresses, I move along this path, which happens to be a line, until at t equals 1, arbitrarily chosen, I'm at 0.33. So this suggests that my line, I need the starting point, which is 1, 1 in this case, plus t times a direction, sort of like a velocity kind of thing. But the direction then is going to be my ending point minus my starting point. So in this case, it's 3 minus 1 in the x direction and 3 minus 1 in the y direction. So my parameterization L of t is equal to 1 plus 2t, 1 plus 2t for t equals 0 and 1. T goes between 0 and 1. And I don't know if it makes you feel better. Sometimes it makes me feel better. Just to be consistent with my notation here, instead of putting L of t, I just renamed it C of t. The next step is to calculate C prime of t. So here I have C of t, which means C prime of t, the derivative of the x coordinate with respect to t is 2, derivative of the y coordinate with respect to t is 2. Step 3 is to compose my vector field f with my curve C. So I want my x coordinate I want to compose that with C, my y coordinate with C, and my z coordinate with C. So in other words, f then, I'm going to plug in for my x coordinate 1 plus 2t, and for my y coordinate, I'm going to plug in 1 plus 2t. And if I don't usually use these basis vectors, so I just rewrote this here in kind of coordinate form. Now f then, if I need to look for my definition of f, for x coordinate, it takes x minus y. So I'm going to have my x minus my y. Here is 1 plus 2t for y, and that's in the x direction. For the y coordinate, I'm going to have x plus y. So I'm going to take my x, 1 plus 2t, and I'm going to add y, which is also 1 plus 2t, and that's in the y direction. So here I get 0 in the x direction and 2 plus 4t in the y direction. So this is f composed of C. Finally, my last step is to plug into this formula here. So I'm going to plug in, and I rewrote the formula here. So work is equal to the integral of C dr dot f is the integral between 0 and 1, and these limits of integration I get from my parameterization. So it's important in your parameterization to always include the range of t. So 0 and 1, and then I need my f composed of C, which is over here, my 0 plus 2 times 4t, and then my C prime. I actually switched the order of these two. But anyway, here's my C prime, and I take the dot product. So taking the dot product, I get 2 times 0 plus 2 times 2 plus 4t, which is equal to the integral from 0 to 1, 4 plus 8t dt, which gives me a final answer of 8. We've just completed this example here, and then because parameterization of our path is so critical to doing line integrals, I have some other parameterization of curves. So we'll discuss the line a little more, we'll discuss a circle, and then also a curve when it's given by this function y equals f of x. And these are the formulas we have. I have them all written here, but we'll give discussion of that next. We are going to start by looking a little bit closer at parameterizing a line from a point AB to a point CD. And we're going to parameterize with the variable t, and we're going to draw a line. So we'll denote our line with an L. The idea of a parameterized curve is that you think of having a curve and you think of tracing this curve out in time. So maybe at t equals 0, you're here, I don't know, driving a car or with your pen, and then at t equals 1, your pen moves here, t equals 2, your pen moves here. So over time, you're tracing out this curve. So that's the idea of a parameterized path, and often we parameterize with t to suggest time. So our equation for a line parameterized by the point t is, first we need a point on the line, and then we need t, our time, times a direction vector. So the point on the line, you can either use AB or CD. I chose to use AB, plus t, and our direction is going to be our ending point minus our starting point. So that's C minus A for x, and D minus B for y. To see why this is the case, we're going to use an example. And we'll use the line from 1, 2 to 3, 3. This is similar to the example we did, but I wanted to make at least the second number different so you can tell. But anyway, so we're going to trace a path from the point 1, 2 to the point 3, 3. And I'm going to claim that the direction, if we're going of this arrow here, is given by 3, 3 minus 1, 2, our ending point minus our starting point. And to see that, I'm going to draw our vector 3, 3. So just drawing the vector here. And then I'm going to draw my vector minus 1, 2. And so that's this point over here, minus 1, 2, and the vector. If you recall from vector calculus, when you combine or add vectors, you essentially use the parallelogram law, or you can think of moving the start of one vector to the tail of the other. So here is going to be, or you can think of completing the parallelogram, and then this vector here, the resulting vector of your parallelogram, or also the vector that ends when you just kind of concatenate your two vectors. This here is the vector 3, 3 plus minus 1, 2. And to more clearly see, that is the direction of the vector going from 1, 2 to 3, 3. Remember, vectors we can move around. They don't have to stay at the origin. And you can see if I moved it up, when I move it up, if I had drawn my vector really carefully, you can see that is the direction of 1, 2 to 3, 3. So that's just, again, this is just, this whole drawing, this example, is to show that the direction of the vector from 1, 1 to 2, 2 is indeed our CD minus AB, our ending point minus our starting point. The next curve we're going to parameterize is y is some function of x. So y is some function of x is equivalent to the ordered pair x, and then y is f of x. So this is it. This is the parameterization right here, where the variable of our parameterization is x, no longer t, but x. If it makes you feel better, you could parameterize this as t and f of t. And the reason why this works, let's say, for example, our curve is equal to y equals x squared. So c is going to be x and our x coordinate, and x squared for our y coordinate. And you can see we made this table of x and x squared. So when x is equal to negative 2, then y is equal to 4. When x is equal to negative 1, y is equal to 1. When x is equal to 0, then y is equal to 0. When x is equal to 1, y is equal to 1. And when x is equal to 2, oops, wrong color, y is equal to 4. So you can see, as I had mentioned, we're parameterizing our curve with our variable x, and as the x progresses, you can see that y follows this parabolic curve, which was given to us in our equation y equals x squared. To summarize, if you have a curve given to you in this form where y is a function of x, your curve then is parameterized by x and then that f of x function. To parameterize a circle, we are going to use polar coordinates. So to parameterize a circle of radius r, we're going to have c, and theta is going to be our parameterizing variable. So as theta progresses from 0 to 2 pi, and those are the limits of my integration, then the polar coordinates, r cosine theta, r sine theta, will trace out a circle. And you can see this, I kind of made a little chart of different values of theta from 0 to pi, and really for the full circle we need to go to 2 pi, but I got lazy and only traced out half a circle, and then I put the cosine and sine theta, so I also got lazy and I just made r equal to 1, radius 1. So when theta is equal to 0, then our x is 1 and y is 0. So we start off here. And then as theta progresses over time and gets to pi over 4, we're at square root of 2 over 2. So we progress from here to here. And then when we're at pi over 3, we get to 1/2 square root of 3 over 2. And when we're at pi over 2, we get to 1, 0. When we're at 3 pi over 4, you can see I made a big jump because I guess I'm lazy. Negative 2, negative square root of 2 over 2 with 2 square root of 2. So something over, this is over here. And then at pi, at theta equals pi, we get back to 0, negative 1. So you can see I've traced half a circle. And if you really, oops, I should really make this a little better. And if I really wanted to see the circle, I would have done more intermediate values, except I didn't. So there you go, because I was lazy. So again, here is our parameterization of the full circle. And as you can see, if you wanted only half the circle, you would just stop from theta equals 0 to pi. Or if you wanted this half of the circle, you would only go from theta equals pi over 2 to 3 pi over 4. There is one other thing I wanted to show you is the composition of a vector field f with c. And I'm just going to use the vector field from our last example. So f is equal to x minus y in the x direction, x plus y in the y direction. So f composed of c. So f, and often what I do is I directly plug in my c, my x variable here, and my y variable for c here. And then I want to do f on my x and y. So my x component is going to be x minus y. So this will be x minus y, r cosine theta minus r sine theta. And then for my y component, I'm going to have x plus y. So this is x plus y, r cosine theta plus, this should be r, I was thinking of complex numbers, I don't know what, y, r sine theta. My next example, suppose f is the vector force field f of x, y, z equals x cubed y, z, also written in this form, x cubed ex hat, y, ey hat, plus z, ez hat. I don't actually like this notation so much because I can't easily type in a hat using the software I'm using to make videos. So anyway, I like this notation more, but you should be used to this as well. So the path is a circle of radius a in the yz plane. So let's be careful with this. We want to find the work done by f while moving along the path. And the first step is to parameterize the circle, but we want to make sure we're going to use the polar coordinates as we had before, but now we have c is a three-dimensional, in the three-dimensional space, except the circle is happening in the yz plane. So this is what our parameterization is going to look like. C of theta is equal to 0. The circle is not happening in the x-coordinate, but in the yz plane. Circle of radius a, so I have a cosine theta, a sine theta, and theta is going to be between 0 and 2 pi because we're drawing the complete circle. The next thing I'm going to do is compose my f, I keep forgetting this, with my path c. And to do this, I often like to write f and then put in the x, y, and z from c. So it's 0, a cosine theta, a sine theta, and then f is equal to x cubed in the x direction, and that's just 0, or rather 0 cubed. In the y, the next coordinate is just going to be y, so it's going to pick the y coordinate for y, and then the last coordinate is just going to pick the z coordinate, so a sine theta. So this is f composed of c. The next step is to calculate c prime. Actually, I switched the order of 2 and 3, but that's okay. They're kind of independent. So c prime of theta, where's my c? It's over here. So that's going to give me 0 minus a sine theta and a cosine theta. And then my last step is to plug in the formula. So I have my work over c dr dot d theta. So I also put in this, I filled in the circle here because we are in a closed path. Technically, if you don't put it in, it's okay. It's still correct, but we're going to highlight the fact that it's a closed curve. The limits of integration are here, 0 to 2 pi d theta, and then I need to dot my f of c and my c prime. So where's my f of c is over here, 0. Oh, I actually did c prime first, sorry. Sometimes I switch the order. This is my c prime, 0 minus a sine theta, a cosine theta, and then my f composed of c, 0, a cosine theta, a sine theta. You can check my calculations when I do my dot product and I do my integration, and I will get a final answer of 0. But that's not unexpected since F, and I forgot my field, is radially out. That is, here in the x component, it's going out of the x, out in the y direction, out in the z direction. So it is perpendicular to the circle. Right, this is our F. Here's our circle. So work done is 0 along the circle. I do have one other parameterization for you, and that's the helix. I have the drawing of it here. So if you look at this parameterization and you look at this helix, essentially what you have here in the x and y coordinate is a circle. And the difference between this and a circle is now the z coordinate increases as theta increases. So it's sort of like you have this circle and you're ever increasing in height. So that gives you that helix over here. And this is a helix of radius 1. Last, your book very briefly mentions the line integral operator over other objects other than just vector fields. There's this scalar and also this cross product, and I did not cover these in my video. To review what we did cover, first we looked at integral operator notation. So when we write an integral, to highlight that this, we can think of this as an operator on our function f of x. We put our integral notation in front and then our f of x. So we think of the integral operator operating on a function. Next, we talked about line integrals, and our example, or one of our main illustrative example, is work that a force F performs as it moves along a path C. And we notate this line integral with the integral over C of dr dot f, where here we have our integral operator on our vector field f. Our dr here is the differential of the displacement vector. So we talked about if we have this curve C here, we can think of r as our displacement. So it tells us where we are on our curve C. Maybe at time t we might be, r might be this vector here. At time t plus 1 we might be here. At time t plus 2 our r vector is over here. And dr then is the vector tangent to the r vector. I didn't draw this very well. This should be 90 degrees, but it's tangent to each point of C. If C is a closed curve, we write the operator with the circle in the middle. And then we also have this index notation here for dr. Again, r is the displacement vector, so think of that as x1, that's the x coordinate, x2 is the y coordinate, x3 is the z coordinate, so you can think of that as dx1, dx2, dx3 in the x, y, and z directions. And we dot that with f, and you remember f is a vector field, so it takes a vector and it produces an f vector. So if we're in 3 dimensions, f produces an f1, f2, and f3. So this is our dr dotted with f1, f2, f3. In index notation then, since we have the same indices, we could do dxi, f of I. We outlined the steps for line integrals. The first step is to parameterize your path. The second is to calculate the derivative of your path, sort of like the velocity. Then we calculate f composed of c, and remember that's because f is defined over the whole space, but we're only concerned about f on our path c. And then we plug into our formula. So the line integral is going to be the integral from a to b, where a to b are your limits on t, and then we have f composed of c dotted with c prime of t. And we worked out this example here in the video. We also did some parameterization, some common parameterization of some common curves. We did a line, a circle, and a graph or a curve given to us by a formula, y equals f of x. So the line from a to b, the line from AB to CD is parameterized by L of t is equal to AB plus t, c minus a, d minus b, where t goes between 0 and 1. A circle of radius r, we parameterized using polar coordinates, so c of theta is equal to r cosine theta, r sine theta, where theta goes between 0 and 2 pi. And if you only want the top half of the circle, theta can go between 0 and pi. If you only want the bottom, then theta is going to go between, if this is 0, pi to 2 pi, etc. And then we have this bonus, the helix. It looks just like the circle, except now we have the x and y drawing the circles, and the z component increases as theta increases. So this would be a helix. And then we also have, again, the curve. If we have a curve given to us with an equation, y equals f of x, then c of t is equal to t, y of t. So it's essentially x and f of x. And that concludes our video. That's it for this video. Thank you for watching.